The last thing that we're going to talk about today is something called the common ion effect. All right, and that's something that's going to affect the solubility of an ionic compound. And so what happens is if you've got a slightly soluble salt and you put it into water that has a second salt that produces one of the same ions, you're going to decrease the solubility of your salt. So let's do an example to see what I'm talking about here. So we have been looking at calcium fluoride in a couple of examples, and so we know the KSP for calcium fluoride is 3.9 times 10 to the 11th, 10 to the negative 11th at 25 degrees. And so what we're going to do is we're going to calculate the molar solubility of calcium fluoride at 25 degrees in a solution that already has some calcium nitrate in it, and the concentration of calcium nitrate that's already in that solution is 0.010 molar. All right, so we've got calcium nitrate already in our solution, and now we're going to add calcium fluoride and look at the solubility. And we want to keep in mind that without a common ion, if we just had calcium fluoride, the molar solubility would be 2.14 times 10 to the negative fourth moles per liter, and we solved for that in a previous problem. All right, so here's the information given to us in the problem. So here's the KSP again. And then we know that our solution already has 0.010 molar calcium nitrate. We want to keep in mind that when this calcium nitrate dissolves, this is very soluble because it's a nitrate, it's going to completely dissolve, that 0.010 molar calcium nitrate is going to correspond to that same concentration of calcium ions because one calcium ion forms for every one calcium nitrate. If we were talking about the nitrate ion concentration, the concentration of that would be 0.020 because there's two nitrates here for every one calcium nitrate. All right, so always a good idea to start with the equation of what's going on. So we can show the dissociation of calcium fluoride and the equilibrium that it sets up. And then again, ice table. We're going to ignore the calcium fluoride. That won't be involved in our equilibrium expression at all. And now here's where the difference is going to come in. This calcium nitrate means that we already have calcium ions in our solution. So our initial concentration is going to be 0.010 for calcium. Now this doesn't have any fluoride, so we're still going to start with no fluoride initially. Then we're going to add X amount of calcium ion as our calcium fluoride dissolves. And we're going to add 2x fluorides as our calcium fluoride dissolves. So in our equilibrium column, we add up I plus C. So we get 0.010 plus X for our calcium ion concentration and 2X for our fluoride ion concentration. Now we just need to plug all of this into our equilibrium expression. So we've got KSP equals calcium ion concentration times fluoride ion concentration squared. Now we're going to plug in what we know for KSP, and we're going to plug in what we know about our equilibrium expressions here, and we can solve for X. So we're going to get 3.9 times 10 to the negative 11th equals 0.010 plus X times 2X squared. All right, now if we try to solve for X in this way, we're going to get a quadratic equation or something that's got like a cubic root and then also an X. The math is going to get complicated. So we're going to make the same assumption that we did in our equilibrium calculations last week. And that's to say, if we've got a very small number here, which we do, it's 10 to the negative 11th, then we can assume that we're not forming very much calcium and fluoride here. So we can use that small x approximation and say that whatever contribution we get to the calcium from the calcium fluoride is going to be really small. And essentially at equilibrium, we can assume that we've got about the same amount of calcium that we started with. So we're going to make that same small x approximation, ignore that plus x, and then we can just solve for x here. So 3.9 times 10 to the negative 11th equals 0.010 times 4x squared. And then when we solve for x here, we're going to get that X equals 3.1 times 10 to the negative fifth. All right, so this is already, because it's a concentration, it's already in units of moles per liter. And we can see that this number here, this molar solubility, is less than the amount that we had before. So last time when we calculated our molar solubility of calcium fluoride, I think it was 2.1 times 10 to the negative fourth moles per liter. All right, so you can see that the presence of the calcium already in the solution made our solubility of calcium fluoride go down. So not as much calcium fluoride could dissolve because there was already some calcium in the solution. All right, so the last thing I want you to do is try this last problem on your own. So it's similar. I've given you the KSP for manganese hydroxide, and I want you to calculate the molar solubility if you put that into a solution that already contains 0.020 molar sodium hydroxide. So go ahead and solve that problem, and then I'll show you the answer in just a second. All right, so here we've got our manganese hydroxide dissociating into manganese ions and 2 hydroxide ions. And again, the problem told us that we already had 0.020 molar NaOH, which means that we would have 0.020 OH concentration. All right, we don't have any manganese to start with. We add plus X and plus 2X, and then we add the I and C columns together to get our E column here. Again, we're going to plug into our KSP expression. So we know that our KSP is 1.6 times 10 to the negative 13th. Manganese concentration is X, and OH concentration is 0.020 plus 2X, and all of that squared because of the coefficient of 2 in our equation up here. We can still make the small x approximation to make the math easier here, so we're going to ignore this plus 2x. So you can see here I've gotten rid of that. And then I'm just going to solve for x, and I get that my solubility is 4.0 times 10 to the negative 10th moles per liter. All right, so like I said, having this common ion present is going to decrease the solubility, so it's going to make this number smaller. But it's not going to change the KSP. The only thing that can change the KSP is changing the temperature.